Torque problems also involve systems where there are multiple supports for distribution of weight. Our first set of problems, all the ruler problems, all dealt with basically having one support, a pivot point somewhere, and then you had weights on either side, and you wanted to bring things into balance. What this set is looking at is having, say, two supports, such as in this picture here, we have a sign that's got wires on either end to support the sign, as opposed to just one wire. And really, what torques can help us do is look at the distribution of weight. We can talk about, for instance, how much tension is in each of the wires that hold up the sign. And really, what it comes down to is if everything is uniform, then the two wires, the two chains would equally divide up the weight that they're supporting. But if things are not totally symmetrical, then there'll be a little bit of difference in the weight that they support. So, here we got a picture with a sign. It's got a bird. Bird is not massive compared to the sign, but it is going to adjust the symmetry, if you will, a little bit. And if we consider our forces, first of all, the bird, the sign, none of it's moving. So all the forces up, the tension in each wire, and the weights, the forces down, well, they have to balance because it's not moving. It's not going up or down. And so the tension, T1 and T2, has to equal the force of the sign, the weight of the sign, and the force of the bird, the weight of the bird. Now what we're adding to that is, okay, we can also consider torques because, for example, if either wire were to break, then the rest of the sign would swing in a circular type fashion. It would pivot about the wire that it's still connected to. And so we can think in terms of clockwise and counterclockwise torques. Now, in this particular case, if we decide the pivot is at the center of the sign, and we're doing clockwise torques versus counterclockwise torques, please note that, again, we're putting the pivot right here. So we don't have to worry about the weight of the sign in that case because torque is force times distance. So if the pivot's at that center of mass of the sign, the distance is 0, you have no torque for that. So what would we have? Well, we would have these two, the weight of the bird going down, and from this position, that would be going in a clockwise direction. And the tension in the wire is pulling up, and so it would tend, again, about this point, it would tend to rotate around that one. And so we have two clockwise torques, and then the tension in this wire would tend to go the other way in terms of the force it's pulling upward, and so that's the counterclockwise. And so basically this gives us two pieces of information to try to solve these problems. And so what we're going to do is just run through a couple of examples so you can see how they're solved. And we're going to start with the picture we have here, in which basically we're going to say that the sign has a mass of 15 kilograms. The bird's only 250 grams. Let the sign be 150 centimeters across with each wire 10 centimeters from the nearest edge of the sign, and the bird 30 centimeters from the right edge of the sign. We want to find the tensions in each chain. Find T1 and T2. So this is the first problem we're going to look at. And just like the ruler problems that we were looking at before, it is really important to make a diagram. So let's start off with that. So, here's our sign. We've got wires on either end. So we're just simply T1 and T2. We have the weight of the sign, and I'm just going to use Fs for just the force of the sign downward, and then we got our bird. Now, so I have the various forces involved. Now I want to make sure and include all of the distances that's involved. Now, here's the deal, of course. I can put pivot point anywhere I want. Okay, I'm not limited. So in this particular case, I'm going to recommend putting the pivot point right here. And so all the distances that I want to be looking at are going to be based on that. One of the nice things about putting it on the left side like that is that all the ones that point down will be in a clockwise direction in terms of rotation about this point, and all the ones that point up will be in a counterclockwise. So it's really easy to keep the counterclockwise and clockwise torques separate. Now, let's see, we had this distance here would be 10 centimeters. And let's see, the whole thing was 150. So that means, we're going to assume the center mass of the sign is halfway. So that would be 75 centimeters, which would make, we'll put it up here. And I mean, obviously the picture can get a little bit busy, but we want to, make it easy to figure out all the things that we have. The birds over here, we said at 30 centimeters from the right side. And then this was also 10 centimeters. And it just kind of depends how you want to label it. It's up to you. So for instance, I could do all the way across. That's one way of doing it. I could also just go ahead and say, well, hey, if the whole thing is 150 and this one's 10 in that way and that's 10 in that way, then this part has to be 130 centimeters. And I just want to make sure I know where everything is. So it's really important when you're doing these kind of torque problems that you've got a diagram, you know what all the masses or weights that are involved, they're all labeled and where they are, and you have enough information that you can now answer your question. So first off, as I said, it's not moving. There's no translational movement. There's no up or down, so that I know the forces up have to equal the forces down. Well, the forces going up, those are the two wires, the tension in the two wires. And then the forces down. Now, in this particular case, I gave, this one is 15 kilograms, and the bird was 225 grams. So I don't actually have their forces yet. I need to do mass times gravity to get their forces. So for the sign, 15 kilograms times 9.8. And then for the bird, it's only 225 grams. So that's 0.225 kilograms times 9.8. And so all of that together is going to be, well, let's just go ahead and do it separately. This one's 147 newtons. The other one is 2.45. And so 149.45 newtons. So the two wires are supporting 149, almost 150 newtons altogether. Okay, but we do not know, because the bird has landed where it has, exactly how that's distributed across the two wires. That's what we're trying to figure out. So now we're going to look at clockwise torques equal the counterclockwise torques. And again, since I put the pivot point right here, these two will rotate in a clockwise direction. In other words, they would rotate this way about that pivot point. They're pointing down. So those would be my clockwise torques. And T2 tending to pull up, well, that would be rotating this way about that pivot point. So that would be the counterclockwise. So I have my 147 newtons. Now its distance from the pivot point, it's in the middle at 75. Okay, but this is in 10, so that's 65 centimeters. And then I have the bird with its 2.45 newtons. And okay, what's its distance? Well, let's see. The whole thing between the two wires is 130. This is 10. That makes this 20. 130 minus the 20 gives us 110. And then that's it for the clockwise torques. The counterclockwise torques, well, that's T2, and it's 130 centimeters. Now, I can also make all those distances meters instead. But since they're all in centimeters, I'm okay, because centimeters will cancel out the centimeters. So put all those things together, and let's see, what am I going to have? So this side will come out 9824.5 Newton centimeters. Divide both sides by the 130. And I'm going to end up basically the T2 is going to be 75.6 newtons. And then to find T1, well, T1 and T2 altogether is 149. So T1 has to be the total, 149.45. Subtract T2. And basically, T1 is going to be 73.85 newtons. And so I have found the tension in each wire. And again, please note how that uses our F-net principles in terms of forces. We got forces up, forces down. It's not moving, so the net force has to be 0. But we're also bringing in our rotational torque to help us look at the distribution of those tensions, the distribution of weight, and how that affects how much each wire is actually supporting. Now, the bird's not very much, so they're slightly off of halfway. Okay, so part of it's just going to depend on the distribution of the weights involved. Any questions? All right, we're going to look at a second case now. We have a boy and a girl on a swing. The boy is 675 newtons. The girl is 450 newtons. It's a 200 Newton porch swing. The swing itself has weight. It's 2 meters long. If the swing is suspended by a chain at each end, what is the tension in each chain when the boy sits 0.75 meters from one end and the girl 0.5 meters from the other end? So again, we're just looking at how is that going to affect the tension in each chain. So just as before, really important first step. I'm going to make a drawing. And it's not really that the drawing has to be any particular size. We just want to make it big enough so that we can label everything and see what's going on. So again, I have 2 chains, one at each end. The swing itself is going to have its center of mass, unless it tells you otherwise. We're always going to say it's at the center. And so, let's see, it said it was 200 newtons. And then we got the boy, and he was 675 newtons. And then the girl, 450 newtons. In this case, the problem gave us everything in newtons, so we don't have to worry about that. Let's see, what other information? Now we want all our distances involved. Well, the chains are at each end. So that's 2 meters. We've been told that that distance will be 0.75 meters. We're going to assume that, again, if we're not told otherwise, the center of mass will be in the center. So that would be at 1 meter. And then the girl, so that was 0.5 meters. And so now I have where everything is located. So, again, F up equals F down. So the forces pulling up, well, that's just T1 and T2. The forces pulling down, well, I have the boy, the swing, and the girl. So in sum, the 2 chains are holding up 1,325 newtons. Now, as I did in the previous problem, and you can do it anywhere you want, I'm going to put the pivot point here. And again, the reason I like putting it in that particular spot is all the arrows going down will represent clockwise torques. All the arrows going up will represent counterclockwise. I can literally put the pivot point anywhere I want. But one of the nice things about putting it at either T1 or T2 is I have zeroed out that particular force in terms of torque because its distance from the pivot point will be 0. So, do it down here, clockwise torques equal the counterclockwise torques. So all the ones pointing down are going to be clockwise. We got 675 times 0.75. We have the 200 times 1 meter. We have the girl, 450 newtons. And now, the whole thing's 2. She's in half a meter from the other side, so that'll be 1.5 meters. So all of that is the clockwise torques. Multiply, add it all up together. Looks like we're going to get 1381.25 Newton meters. And again, torque will always have basically force times distance for its units. Now, what about the counterclockwise ones? Well, there's only one going up, that's T2, and T2 is 2 meters away. So, setting these two together, we're going to end up with 1381. Divide both sides by the 2 meters, and there is my T2. To find T1, well, that's just going to be the total, subtracting the T2 I just found. And there we have one of them at 690. The other one is 634. Not quite equal anymore because all the weights involved are significant compared to each other. And so that is our second example. Any questions? All right, we're going to look at one last example, which really isn't different, but it might feel different just because of the way things are set up. What we're going to look at this time is what I call the bridge problem. We have a bridge, and it is supported by pillars. In this case, we're going to say supported by pillars that are 5 meters in on each end. The bridge is 50 meters long. Bridge weighs 400,000 newtons. There's a 2,500 kilogram car. It's parked 10 meters from one end of the bridge. How much force does each pillar exert? So it's really not different from the previous problem, but it feels different because it's, I'm talking about a bridge and there's a car on it versus boy and a girl on a swing. So, again, let us start with our picture. And really, again, don't make your pictures too small. You want to have plenty of room to label things. So, and I'm just going to call these F1 and F2 because basically this is forces holding everything up as opposed to chains or wires. It's a uniform bridge, so again, in the middle will be its center of mass. Bridge, of course, is much heavier than the car. We've got a car closer to one end, 2,500 kilograms. So there are all the force-related things. Now let's get our distances in. So we know where everything is. And I'm not really using the ruler for measuring purposes. It's just makes nicer straight lines. That's the main thing. So we know that each pillar is 5 meters in. Let's see, the car was 10 meters in. So, I'll just put another 5 meters right there. That's still consistent with it being 10 meters from that side. Just depending on, how much information you want to put into your diagram, you could, do one for halfway if you wanted. It just kind of depends. You just want to make the diagram so it's usable. And so now I have my picture. Now, the car is in kilograms, so the force of the car, well, that's going to be 2,500 kilograms times the 9.8. And that'll come out 24,500 newtons. So, let's see. Again, start up with F up, F down. So, F1 and F2 are the ones pushing up. And in this case, all I've got is the bridge. And the car. So, in total, the two pillars are supporting 424,500 newtons. Now, just to kind of change things up a little bit, I'm going to go ahead and put the pivot point over here. As I said, it can be anywhere you want. Okay, all that matters is that once you pick it, you do all your distances in relation to where the pivot point is. And secondly, you want to pick one of your unknowns. I don't know F1 or F2. I want to pick one of them because then it's zero distance from the pivot point, and it won't be involved in the torque calculation. Okay, so clockwise equals counterclockwise. Now in this particular case, because I put the pivot here, okay, F1 will be the only one that goes in a clockwise direction. And its distance, well, they're in 5 meters on both sides. So there's 40 meters between them. Now, in the counterclockwise, both of these guys are going down, but with that being the pivot point, they would rotate around that pivot point this way, which is counterclockwise. So I have the 400,000 newtons. And, again, it's at halfway. That's 25. This is N5. So that would be at 20 meters. The truck, 24,500. Well, it's only 5 meters away from that second pivot point. Go ahead and put some things together now. Divide both sides by the 40. So there is F1. F2 is going to equal the total, subtract F1. So F2 ends up being that's how much weight it's actually supporting. And honestly, it should make sense from the standpoint of the car is closer to F2. F2 is supporting more of the weight than F1 is. And so, some examples of doing torque problems, but now, as opposed to arranging things so it's all in balance, it has to all be in balance because nothing's moving, but the weight is distributed unevenly because everything is not totally symmetrical. And so hopefully this will be helpful for you when you look at the homework, Torque Problems 2, that will be due Monday.